Okay.
Matter of fact, I think we can do the pump to pump show.
Okay. Yeah. Well. Yeah. Okay.
So Hannah's REU student. Did work on that stuff.
Hey y'all, I'm Hannah. I'm the other REU student working in Dr. Wright's lab, actually, and I worked on post-precipitation nitrous oxide emissions this summer. When we do nitrous oxide emission work and general greenhouse gas emission works with agricultural emissions, we generally go out and sample 1 to 2 times a week, depending on what stage of growth the crop is in. And then if it rains, we'll go out the morning after and take samples, as there's a bump in emission after rainfall as water replaces airspace in the soil and it creates anoxic conditions, which prompts denitrification. So my job was basically to go through and take a ton of samples after it rained, after simulating rainfall, so that we could check and see whether going out the morning after actually works to capture that bump. Because once you start getting to larger bumps that happen, it could get to a point where it might be obscuring treatment effects. So I work with corn that is planted at KSU North Farm, which is a silty clay loam, and it's a no-till. We applied broadcast urea at 168 kilograms per hectare. That's 150 pounds per acre. And you can see in the top corner, my chambers right there, we installed 6 of them so that I can have 6 replicates. And then we simulated rainfall by hand early in the morning. And then we started collecting gas samples immediately after finishing that hour of precipitation, and then in 8-hour increments for the next 48 hours. For the runs I have the full data on, we did a wet run. So we started with soil that had already been moistened, and I have here some of the antecedent data collected from right before we added the precipitation. As you see from my results, after an initial lag period, nitrous oxide flux levels generally follow the trend of soil moisture. So when the soil is wetter, more nitrous oxide is being released, and then as it dries out, those flux levels slowly drop back down to normal. I then use a polynomial regression to calculate a nice curve to follow the emissions under, and then integrated it to begin comparing the actual or most close estimate of the true emissions over the 48 hours compared to what we would get if we extrapolated from one sampling event. So I looked at 8 hours, 16 hours, and 24 hours after precipitation to estimate what would happen if you went out just the morning afterward. And I found that 24 hours has virtually no impact, which is a great thing to know because it's not realistic on larger scale experiments to go out this many times over 48 hours. On some of our larger experiments, we collect 150 samples at each event, so that racks up really fast. I found that sampling 8 hours tends to be the worst time, as when I did it, we had 112% overestimate of the emissions released, which gets to a point where it can start causing problems with figuring out treatment effects. And then I don't have it here, but if you go further after 24 hours, it also you start very heavily underestimating the amount of emissions you get. And some areas for further study would be conducting the experiment multiple times to confirm the results I got about 24 hours, as well as I would like to go in the first 10 to 12 hours, taking samples more often to clarify that one dot that we have that's super high and figure out exactly what's going on in that first time, as we know the peak happens relatively quickly in wet soil conditions. And so I'd like to double check whether that's an outlier or whether there's more of a peak that we're missing. That's all for me. I'd like to thank Dr. Rice, my mentors, Arosha and Wagner, who unfortunately weren't able to be here today, Casey, who was another undergrad worker who went out with me at all hours of the day to go take samples, and the Soil Micro Lab and the Rain Network. Thank you.